Swayam Prabha. Digital India. Educated India.
Hello and welcome back to the series of manufacturing automation sessions. So, I would like to remind you that last time we started discussing the precedence diagram for the automatic assembly, and it was said that the precedence diagram helps us in find out the different ways of getting the assembly. Let us take an example of this small assembly, which is the power plug assembly, and we said that the any assembly, small or big, it is better to have on a base plate. So, this is the base for the assembly of the power plug. On the base, we are trying to assemble the ground pin, fuse clips, neutral pin, live pin, cord grip screws, and then the cover. So, let us see how the precedence diagram helps us in finding out how many ways the assembly can be performed. So, in the precedence diagram, each activity is given a number and this is circled. For example, this 1 is the load base onto work carrier. Since nothing can be done without loading the base onto the work carrier, all the arrows are going from 1 to 1A, 2, 3, 4 and 5. Well, 2 is the ground pin, 3 is the neutral pin, 4 is the live pin, 5 is the fuse clip. Now, with the dotted line, the sub assemblies are being shown. For example, 1A is the cord grip, which is this. 1B is the cord grip screws, which are coming from the other side, and 1C, this is the cord grip screws as well. So, since the cord grip screws will be coming from the other side rather than the cover or the cord grip, for example, therefore, 1A, 1B and 1C, they have been shown in the dotted line, which will be a sub assembly. So, after that, when the load base onto the work carrier, the second column will be 2, 3, 4, 5, that is ground pin, neutral pin, live pin and the fuse clip. Now, this is given in one column, saying that 2, 3, 4, 5 can be made or can be assembled in any order. So, that is why it is given in one column. All right. After 2A is given as a sub assembly, because 2 is the ground pin and 2A is the ground pin screws. For example, this is the ground pin and these are the ground pin screws. So, ground pin and ground pin screws can be made separately as a sub assembly. Similarly, the neutral pin and the neutral pin screws, this is the neutral pin and the neutral pin screw can be made as a sub assembly separately, and then the whole entire sub assembly can be put here on the base. Now, 5 and 5A, 5 is the fuse clip and these are the fuse clip screws. So, it can also be made as a sub assembly. Then it is 6, which is the fuse. After the clips are made, so the fuse is mounted or assembled. After that, this is cover, then it is the cover screw and then remove complete assembly. Now, as you can see that these are subdivided into columns. For example, 1 is in one column, column number 1, 2 in column number 2 we have the 2, 3, 4, 5, as I said that they can be made in any sequence and so on, but then 7, 8 and 9 they are separately standalone, in the sense that there is no alternative of 7, 8 and 9. So, 7 has to be done first, then 8 and then 9, because as you can see that first cover has to be put, cover has to be assembled, then the cover screws can go from the other side and so on. So, there is one point here in the assembly process, that if the assembly is very big, meaning that there are a lot of parts to assemble, in that case not to have the large number of assembly workheads and the assembly machine, many times what is done is that assemblies are broken into small sub assemblies, and the sub assemblies are made in a line. After that, all the sub assemblies will be put together as an assembly. So, in that case what is happening is, for example, here as you can see, this sub assembly example will be 2 2A, or 1 1A, 1B and 1C, meaning the load based onto the work carrier, cord grip screws and cord grip screws separately. So, they can be made as a sub assembly. So, for that, for example, in this case the number of workstation will be only 4, okay, or maybe it is 3, because the cord grip screws can be made in one for both of them, 1B and the 1C. So, therefore, we divide them into sub assembly, and let us see an example that when this power plug assembly is made into sub assemblies, then how many ways the sub assemblies can be assembled. Let us see that. Here is a precedence diagram for the sub assemblies of the same power plug. All right, power plug is the same, but here it is the sub assembly. For example, 1, it is the load base sub assembly. 2 is the ground pin sub assembly, meaning the ground pin with the ground pin screws made together in a separate place, and then that sub assembly is given here for the entire assembly. Now, why we are giving this example? Because this is a smaller number of parts, much smaller number of parts than it is made in practice. For example, in the automatic assembly of other machines, production machines, there may be thousands or 10,000s of parts. So, to make all those parts together in one assembly, one at a time, it will need a large number of workheads. Therefore, there will be possibility of the machine down. Okay, that means the out of 1000 machines, somewhere or other 1 or 2 machines may not work. But if we make them, if we break these assemblies, bigger assemblies into smaller assemblies of let us say 10 12 parts, then there will be 10 12 workheads only working together, one at a time, I mean at a time. So, in that case the possibility of machine breakdown will be much less, and then production time can be decreased, or production rate could be increased. Let us see this sub assembly. So, 1 is, as I said, that 1 is the load base sub assembly, 2 is the ground pin sub assembly, 3 is the neutral pin sub assembly, 4 is the live pin, fuse clip sub assembly is the 5, 6 is the fuse, then the cover, then the cover screws, and then removal of the complete assembly. Now, as I said, there is no flexibility in the sub assembly of 1, 7, 8 and 9. So, therefore, they are given in a separate column. Now, 2, 3, 4, 5, they are given in a in one column. So, therefore, there is a flexibility in the sense 2, 3, 4, 5 can be made in a different way. So, between 1 and 7, 2, 3, 4, 5 and 6 can be carried out in any order, except that 6 cannot be carried out until 4 and 5 are completed. Let us see 4 and 5, live pin and the fuse clip, meaning that fuse which is 6 cannot be assembled before the fuse clip sub assembly and the live pin sub assembly go in. You can see that in here. For example, here is the fuse clip and here is the live pin. So, before the fuse clip and live pin, the fuse cannot go in. So, after the live pin is inserted and the fuse clip with the screws inserted here, then the fuse can go in. All right. So, that is why it is said that 6 cannot be carried out before the 4 and 5 are completed. Next, it can be performed in two ways, like 4, 5 and 6 or 5, 4 and 6, meaning that if we have this, we can do the fuse clip first, then live pin, or live pin first, then fuse clip, and then the fuse can be inserted. So, there are two ways of doing that, first 4 and then 5 then 6, or first 5 then 4 then 6. All right. Operation 3 can be performed at any stage in this order. That means, there are two ways of doing that, and in this order we can do perform the operation 3, which is the neutral pin subassembly, in any way, in any order. So, there will be 1, 2, 3, 4 into 2 ways, that will be 8. So, number of possibilities will be 8 then. Finally, operation 2 could be performed at any stage in the ordering of operations 3, 4, 5 and 6, and earlier it was, we have seen there are 8 possibilities. So, now there are 1, 2, 3, 4, 5 into 8 will be 40 possibilities. So, you can see that for a small subassembly like this, which is a power plug subassembly, we have 40 different ways to do that. Even when we have the 1, 7, 8 and 9, there is no other possibility, they are rigid. So, only in 2, 3, 4, 5 and 6 there are 40 possibilities. So, if we are talking about a big assembly, for example, or big subassemblies for example, there could be many ways, and we can select the best possible way for us depending on our capability, depending on our convenience, we can take the best possible way, and it is all shown by the precedence diagram. This is the advantage of the precedence diagram, particularly when the assembly is very big and a very large number of parts involved in the assembly process. Our next topic, we will discuss the performance and economics of assembly systems. This will be our last topic in this series of lectures. So, what does it mean that when an assembly system works, let us see how effectively it can be exploited, how effectively it can work. So, multi-station assembly machines may be classified into two main groups according to the system used to transfer assemblies from workstation to workstation. So, this we have discussed earlier, like there are two basic groups, either it can be an inline indexing type or it can be free transfer or non-asynchronous assembly machines. Now, in case of indexing machines, as we discussed earlier, we have an indexing table and the workstations are located around that indexing table. Now, the part will go from one station to another station, meaning the subassembly will go from one station to another station indexing, and then it will dwell for some times till the subassembly operation is over in that workhead. Now, in case of free transfer or non-asynchronous asynchronous assembly machines, we do not have the indexing table, and therefore, we have the buffer stock in between. So, therefore, if a machine stops, in that case the other machines may not suffer till the buffer stock is filled up or buffer stock is available. So, indexing machines are those assembly machines in that transfer all the work carriers simultaneously, and a stoppage of any individual workhead causes the whole machine to stop. Now, here of course, the disadvantage in the indexing machines will be that if one machine stops, the other machine will be stopping, but keeping in mind that indexing machines are used for small parts, small assemblies, small machines. So, therefore, we assume that the stoppage of the machines will be rare, and particularly like I said that a big assembly could be broken into sub assemblies and the sub assemblies can be assembled first. So, those kind of small sub assemblies can be assembled in the indexing machines for example. Now, free transfer or non-asynchronous assembly machines, the workheads are separated by buffers, as I said. Buffer containing assemblies and transfer to and from these buffers occurs when the particular workhead has completed its cycle of operation. So, the buffer stock is, as I said initially when we have discussed the buffer stock, it is actually a locking of capital, but it is required particularly in the free transfer machines where a large number of machines are there and the possibilities of the machine down will be larger. So, in this case what happens is that one machine which will finish the sub assembly that machine will keep it in the buffer, and from the buffer the next machine will take up the sub assembly as and when that next machine requires. So, in that case what is happening, that the machine time can be different in two subsequent machines, because the machine number 2 does not wait for the machine number 1 to finish, because machine number 1 will finish and put the sub assembly in the buffer, and from the buffer the machine number 2, that is the next machine, will take up. So, that is those are the free transfer machines. One of the principal problems in applying automation to the assembly process, as we know, is the loss of production resulting from stoppages of automatic workheads when defective component parts are fed to the machine. This we have discussed earlier. So, there could be two things. One is that when a defective part goes in, then the defective part either it cannot go and stop the machine, or it will go and it will make unacceptable assembly. These are the two possibilities which we will discuss here as well. Now, the quality level of the parts to be used in automatic assembly must therefore be considered when an assembly machine is designed, meaning that quality level of the parts should be parts which are going to the sub assembly or the assembly should be high enough so that the machine does not stop or the workhead does not stop. This is the idea here. Let us discuss first the indexing machines and the effect of part quality on the downtime, meaning that if we have different quality of parts, that how the downtime of the machine will depend. That means, we will find out the downtime, for example. Now, in this analysis, let us say small n is the number of automatic workheads, small t is the cycle time, x is the ratio of defective parts to acceptable parts. What does it mean? So, x is ratio of defective parts to acceptable parts means that this actually gives you the quality ratio, that how good a part is, how what type of quality the part will have. X is giving the reflecting the quality level of the parts. M, small m, is the proportion of the defective parts causing machine stoppages, meaning that if m is equal to 1, for example, then all the defective parts going into the machine stop the machine, means that all defective parts fed to the machine would stop the machine. If m is less than 1, in that case not all defective parts will go and stop the machine, but they will make an unacceptable assembly, because the part is faulty. It will not stop the machine, but it will make an unacceptable assembly. Okay? Let us keep that in mind. Now, capital T is the time taken for an operator on an average to locate the failure if the machine stops or the line stops, to remove the defective part and restart the machine. So, if you remember about this, we discussed earlier that this is then an operator will spend some time to find out what happened and then diagnose the problem and then rerun or restart the machine. Capital N is the number of assemblies produced in the line. Therefore, that the total downtime due to stoppages in producing n assemblies will be, depending on the m, that is proportion of the defective parts causing machine stoppage, all right. It may be is equal to 1 or it may be less than 1, that is m. Then it will depend on the quality factor of the parts which are going into the sub assembly, that is small x. Then it will be number of automatic workheads. Larger number of automatic workheads will have the larger possibility of the downtime, that is what we said. So, therefore, the total downtime is a direct factor of the number of automatic workheads as well. Then, depending on how many assemblies we are producing producing more number of assemblies, that means the more time the machines will be working and downtime possibilities will be more. So, it is a direct function of the capital N, which is the number of assemblies produced, and the capital T, which is the time taken for an operator on an average to locate the failure, remove the defective part and restart the machine. So, once again total downtime we are having equal to m x small n capital N number of assemblies and this time for an operator taken. Since each time the machine indexes, all assembly tasks are completed. Mind it, we are discussing the indexing machines. So, in indexing machines, as I said last time, once it indexed, in that case one complete assembly will be obtained at the output. So, therefore, since each time the machine indexes, all assembly tasks are completed and one assembly is delivered from the machine at the output, okay, at the output level. Hence, the machine time to assemble n assemblies, since it is taking small t is the cycle time into the number of assemblies produced. So, the machine time will be n into capital N into small t second. Well, therefore, the proportion of downtime d on the machine is given by the downtime and complete time. So, it will be downtime plus assembly time plus downtime. So, assembly time plus downtime is the complete time taken for the assembly, and since we are finding out the proportion of downtime. So, this will be downtime divided by the total time. So, downtime we have seen that this is m capital N x small n and capital T divided by machine time or assembly time will be capital N into small t, that is the number of assemblies into the cycle time plus the same downtime here. So, that can be simplified equal to m x small n divided by m x small n plus small t by capital T. For standard fasteners such as screws which are often employed in assembly processes, an average value of x might be between 0.01 to 0.02. Now, why we are discussing this x? Because this is the quality level of parts, small x is the quality level of parts. So, here if you can see that the d proportion of downtime is directly proportional to the x, alright. So, therefore, if we can vary this or if we can decrease or increase that, in that case our d proportion of downtime will be changed. So, therefore, we are saying that most of the parts, many of the parts, majority of the parts, small parts are the for example, screws. Okay. So, their x might be between 0.01 and 0.2, 0.02, meaning that out of 100 parts 1 may be defective if it is 0.01, or 0.02 out of 100 parts 2 parts are defective. 2 parts means in this case we are talking about the screws, because these are the small parts which are used maximum. In other words, for every 100 acceptable screws, there would be between 1 and 2 defective ones depending on the value of the x 0.01 or 0.02. So, what will happen that whenever this kind of parts will go, if it is 1 part in 100. So, in 100 cycles 1 cycle will be down, because the screw is unacceptable, meaning that it can go to the assembly, either it can stop or assembly workhead, or it can spoil the assembly. A higher quality level is generally available, but with screws, for example, a reduction of x from 0.01 to 0.005, for example, 0.005 may you can interpret it as out of 1000 there are 5 screws which will be unacceptable, may double their price and seriously affect the cost of the final assembly. So, there is a contradiction. If we are increasing the quality level of the parts, okay, the assembly downtime will be less, but at the same time the cost of the assembly will be increased obviously. So, we have to judiciously judge, we have to judiciously find out that what is important for us, whether the part level can be increased, we will invest more money and then downtime will be reduced, or in some cases we can allow these defective parts to go in, spoil the assembly, okay, but we will not stop the machine. So, these are the two things that we will discuss now. Let us see. Now, if we draw the curve, for example, this is the proportion of downtime and this is the quality level of parts. Quality level of parts is x, alright. So, here the quality level of parts we are telling as out of 1000 there are 5 parts defective, out of 1000 there are 10 parts, 15, 20, 25 and so on. So, here we are taking the proportion of downtime as 0.1, 0.2, 0.3, 0.4 and so on up to 1. So, by the way, proportion of downtime also is expressed in percentage, all right. So, for example, 0.2 is 20%, 0.9 is 90% and so on. The downtime on an assembly machine having 10 automatic workheads is 0.33 of the total time available from the curve, meaning that these curves are made for different number of workheads 5, 10, 15 and 20, and also for some constant parameters of small t, that is the cycle time divided by time taken to for an operator to find out the fault and restart the machine, and then m is equal to 1. That means, all defective parts going into the machine stop the machine, that is the m is equal to 1 I said to you. Now, for example, for 10 having 10 workheads, this will be for an assembly machine of 10, it is 0.33 of the somewhere between I mean somewhere here, let us say. Okay. So, well, for a particular quality level of parts, for a particular quality level of parts, we are saying that you can find out what will be the proportion of downtime for the number of parts, either 5, 10, 15 or 20. Subsequent results, how we can get it and whether we need the large number of machines and what is the difficulty in having the larger number of machines, we will discuss in the next session. Thank you very much.